Okay, everyone, let's get started with today's lecture. So, today what we are going to do is we are going to cover an architecture which is called as the transformer architecture. And before we move into the architecture itself, I want to motivate this lecture by explaining why understanding this is very important for us. So, first of all, let's begin by understanding a brief recap of what all we have done till now. In the first lecture, we started by understanding the difference between explicit versus implicit modeling. And within implicit modeling, we looked at there are two broad classes, which is RL and imitation learning. And since then on, our main focus has been on imitation learning. Imitation learning offers a lot of improvements over RL. It does not require any reward function. It does not have the initial starting trouble. It does not take any exploration into account. We directly learn from human demonstrations. So initially we started by thinking that is it similar to a supervised learning problem, which is a very common technique used in machine learning where you are given input output pairs of data and you have to train a model that predicts the output given the input. And we actually started by doing that. We started discussing functions which can take an observation and predict actions at the end of it. So we decided to use this terminology of observations and actions, which is quite consistent with the terminology used in the RL literature. Now, this is a point estimate policy. Why is it called point estimate? Because one point maps to one point. One observation maps to one action. So it's called a point estimate policy. We realize that point estimate policies do not work well for problems which have multiple modes. That is, there are multiple ways to provide the solution. Point estimate policies simply end up taking average of all these modes. They don't consider that, okay, I have five modes, so all of them have a chance of occurring with different probabilities. That is the biggest problem with point estimate policies. And even though we are still confined within the regime of imitation learning, we then moved ahead from point estimate policies, which is what we see in traditional supervised learning, to deep generative modeling. What deep generative models do is very interesting. They do not predict one single action for every observation, but rather they predict the probability distribution of all possible actions for every observation. And this probability distribution, there is a true probability distribution which we want to predict, which we call P data of X. And there is a predicted probability distribution which our model is trying to predict, which is called P phi of X. Now, this completely circumvents the problem of point estimate policies because it does take into account multiple modes. So from that point of view, it is very useful. Now we looked at one specific class of deep generative models, which is variational autoencoders. What variational autoencoders do is they take these input images. Now remember that we do not have this probability distribution. We don't know what that is. All we have is individual samples of data. So imagine that these are handwritten digits like 2, 3, 7, etc. These images have some underlying factors of variation, hidden factors of variation, like how slant the handwriting is, how neat the handwriting is. All these hidden factors of variation are hard for the human mind to comprehend. We cannot even understand how many factors are playing a role, let's say, in finding a distribution for images of cats. It's an incredibly hard problem. So we say that we don't know this, but we will let the decoder do the job. So this is done by by an encoder. So encoder takes in these images and maps it to a variable which is called as a latent variable. These latent variables are denoted by symbol Z. So Z is a compact representation of the original images. You can imagine Z to be something like a zip file which we have on our PCs. The information, the essence of it stays the same, but the size is considerably reduced and it captures all the hidden factors of variation. Because of the word hidden, it's called latent. Both of them mean the same thing. Now it's not only enough for you to encode the data, you have to finally decode it back, right? So you have a decoder also, which decodes it back, and you get the final sample, which is called as X hat. So you have an encoder and you have a decoder. What does the decoder do? The decoder takes in the individual factors of variation. Like, let's say someone tells me my handwriting is slant and it's not very neat, and maybe I apply this much pressure. Given all the factors, I can pinpoint that this is Rajat's handwriting. So this is what the decoder does. The decoder takes these factors into as the input and predicts the entire image as the output. Now, this image should be as close as possible to this image. And in fact, we do construct a loss based on this, which is called as reconstruction loss. But there is another loss term which is not quite apparent at first, which is called as regularization loss. What the regularization loss term does is it looks at the distribution of the latent variable and it forces the distribution to be as close as possible to a Gaussian distribution. Now, we build an intuition for this in the last lecture, which goes somewhere on the lines of every possible distribution in the world. Let's say you take distribution of cats and you take one hidden factor, which let's say varies in cats. Let's say the amount of fur which the cat has. Now, the intuition goes like there will be some cats which have a lot of fur. There will be some cats which have absolutely no fur. But most of the cats in the world will have the fur level which is somewhere average. So you will have a curve which looks like this. Here you will have low fur. Here you will have a lot of fur here. And then again low fur. So it looks like a Gaussian. Because of this intuition, we force the latent variable to look as close as possible to a Gaussian distribution. And these two terms, they form the loss term in the variational autoencoder. Now, we are particularly interested in robotics data. So in our case, this will not be handwritten digits, but X will be a combination of two things. It will be a combination of proprioceptive data, which is the images, which is the information about the joint angles of the robot. And if we consider the SO101 robot, which has 6 degrees of freedom, this will be 6 numbers. Then we have the observation. Sorry, this whole thing is actually called the observation. Next, we have the images from the camera. And if we consider images which are of the size 480 by 640, and we have 3 dimensions RGB, then the size of these, the number of pixels are going to be 480 into 640, which are the number of pixels in this rectangle, into 3, which are the number of channels. So your observation is going to look like this, which is going to be passed as an input to the encoder. Okay, so finally, we want to look at all these applications in the field of robotics. So even though we are taking examples which are in the realm of text, our final modality is a combination of text and images. So we should always keep that in mind. Okay, now let's take a jump and look at some of the modern robotics architectures. Even if you don't completely understand them right now is totally fine. We will look at one architecture which is called as OpenVLA, which is a vision language action model. Now, this model, at the heart of it, it has this VIT, which is a vision transformer. And we also see something called as a vision language model. Then we look at the ACT policy, which is the focus of this bootcamp action chunking with transformers. Here you clearly see the word transformers written in the policy itself. Then we have small VLA. If you look at the documentation of small VLA, you come across terms like self-attention, cross-attention, then this QKV. And all of this, if you don't understand transformers, it is extremely difficult to understand what the policy is doing. If you don't even know what a self-attention means, what does cross-attention mean, what are these Q, K, and V values. Then you look at Nvidia's foundation, the model, which is Groot, and you look at their page and imagine you are very excited to learn about this and you land upon this image, which talks about the model architecture. So if you give an instruction to the robot which says pick up the industry object and place it in the yellow bin. Now we understand the meaning of this word encode now, but what about this transformer? And there is another word diffusion over here. There is vision language model. So there is a common language being spoken in all of these different architectures, with people who land up in these places for the first time, they would get intimidated by. But there is something which is very common across all these four architectures, which I showed you in a very fast time. And the factor that is common is the transformer architecture itself. So if you understand the transformer architecture with a lot of clarity, when you see such diagrams, you will get a lot of confidence that maybe others won't understand this, but I understand transformers and I understand what self-attention means. I understand what cross-attention means. Then in cross-attention, you can see this Q is not there, only K and V is there. So you might ask the question, why is Q not there here? And why is it only there in self-attention? So all these questions will become very intuitive for you when you understand transformers from a fundamental level. And that is the reason I wanted to devote a separate lecture for transformers in this bootcamp. This will keep on happening, I think, in multiple years to come until and unless people shift from an auto-regressive approach to probably a different approach. But until that happens, transformers is like bread and butter for modern robot learning. And if transformers wouldn't have happened, I don't think we would have all this progress in modern robot learning. We would have still been stuck somewhere in between classical learning, imitation learning, and reinforcement learning. Okay, so now that we have this introduction as a background with us, let us start understanding the transformer architecture in detail. Now, some of you might not be aware of transformers, some of you might have some basic intuitive understanding of transformers. Can I get some idea in the chat with respect to your understanding of transformers? Can you just type whether it's basic, zero, or intermediate? Okay, so for everyone, it's somewhere around basic and intermediate. And it looks like some of them have no understanding of transformers. So it's great that this batch at least has some basic understanding, which helps me in like curating the way I teach. But all right, let's see. Okay, so we will start with a very simple objective, and then we will move ahead. But before we start with that objective, I just want to help you understand which paper started it all. So the paper which is of focus here is Attention is All You Need. This paper came out in 2017, and if you look at the number of citations they have 210,000 citations. Even if you combine 100 professors together in their lifetime, it's hard to achieve these many citations. And this indicates the kind of impact this paper has on the AI community. So you can see at the top they have written this message that Google grants permission to reproduce the tables, and this probably happened because a lot of people started emailing them asking for permission about whether they can use the figures in the transformer paper in their own academic work. So instead of replying to all these emails, they just wrote a disclaimer at the start. So I would really like all of you to take a printout of this paper and read this paper from every single paragraph. This exercise is very important because it's almost like when we are learning mathematics, we learn about addition and subtraction in detail, right? Attention is like that. It's a very fundamental building block in artificial intelligence. So you need to understand the first paper which talked about it. Okay, so the final architecture that we are going to learn today is this. We are going to understand what this figure represents, and it might look intimidating at first, but this is what our goal is going to be. So at the end of it, we will look at all this diagram and we will understand almost the entirety of it. Okay, so let's look at a simple example so that through that example, we will understand the transformer architecture. Okay, so let's say that our task is to teach AI a simple rule. We want to create a system which swaps the adjective and the noun, which means that if I give red car as the input, as an output, I should get car red. If I write red car and blue bike as the input, as an output, I should get car red and bike blue. So this is the task that we have in our hand. And to complete this task, we have to go through several steps, which I'm going to explain right now. The first step is understanding our vocabulary. So we are going to assume that our vocabulary consists of a combination of colors and objects. So you can see that I have written a total of 8 colors and 7 objects. So the vocabulary is going to consist of only these colors and objects. I'm going to not look at anything beyond this. So this is my vocabulary. We are going to look at this analogy in terms of modern LLMs also, but for now, let's just focus on a very small vocabulary to build the intuition. And then we are going to consider some special tokens also as a part of the vocabulary. So the first token that we are considering is called BOS, which is beginning of sentence. And the second token which we are considering is EOS, which is end of sentence. And we also use a pad token to make sure that all sentences in a batch are of same length. So these special tokens will be useful for us when we are actually in the decoding stage. We will get to that, but just keep that we do have these tokens in mind so that the decoder knows when to start generating and when to end generating. If you ask any question to any LLM, then the LLM doesn't just go on a rant and continue to answer. It does stop at some point, right? So how does it know where to stop exactly? So this special token is going to be useful for us to understand that. Okay, so the transformer architecture, which was introduced in the 2017 paper Attention is All You Need, it consisted of two building blocks. The first was the transformer encoder, and the second was the transformer decoder. So this paper which you look at here, the left side is the encoder and the right side is the decoder. We are going to first focus on the transformer encoder and understand the entire architecture of the encoder. Okay, so let us consider this input, which is the red car. Now, what happens in the encoder is very interesting. The first thing that happens in the encoder is every single token or word in this case, like let's say the or red or car. Let's take an example of the. It is converted to something called as an embedding. Similarly, red is also converted to an embedding, and car is also converted to an embedding. You can consider this embedding in an analogy as something like a uniform. We are uh, specifying a uniform for every token in our sequence, and this embedding captures the semantic information related to that word. For example, let's consider that the dimension of the embedding is 3. So this is X, Y, and Z. And let's say you have an embedding corresponding to the word king. Now, because the embedding captures the semantic information, if I look at how the embedding for the word crown looks like, it's probably going to lie somewhere very close to the word king. And if I look at, let's say, an embedding which talks about, let's say, Paris, then there is not much connection. So it's probably going to be a bit far from the embedding for the word king. So you can consider embedding as a vector representation for every single token in the sequence, which captures the semantic information of that token. Now, whenever an input is passed to an encoder, it is not just passed just like that. It is first converted to an embedding as the first step, which is what we have drawn over here. This is one vectorial representation for an embedding where we have assumed that the embedding has 3 dimensions. Now, token embedding is fine. People usually add another embedding to the token embedding, which is called as the position embedding. Now, why is the position embedding required? Let's consider this sentence. If you take this example, the dog chased the car. Okay. And then let's say I change this sentence where I say the car chased the dog. Now, both of these sentences contain the same tokens, and when you convert them to a token embedding, they will probably look something like this. So, this is the token, let's say, this is a dog, this is chased, and then we have car. Now, both these sentences will have the same token embedding, but semantically they mean something completely different, right? The first sentence means that the dog is chasing the car. The second sentence means that the car is chasing the dog. So, whenever we are trying to model sequences or understand sequences, the ordering of the tokens becomes very important. So, along with the token embedding, people usually pass a position embedding also. Position embedding indicates in this sequence, where does this token lie? Is this position 0, position 1, position 2, position 3, etc.? So for example, this is position 0, 1, 2, 3, 4. But in this sentence, the position for the token the is, or the position for dog is 4, whereas in this case it is 1. So the position embedding is going to be different for both these sentences. And people usually add these token embeddings and position embeddings to represent one single vector for each token. Okay, so far what we have seen is that the first step of the transformer encoder, every single token in the sequence is given an uniform, which talks about the semantic information of the token. And this uniform consists of token embedding and position embedding. Token embedding captures the semantic information or the meaning of the word in a vectorial form, and position embedding captures in the entire sequence, where does this token lie? Does this lie in position 0, 1, 2, 3, etc.? That is what it captures. So the first input to the transformer encoder is the token embedding plus the positional embedding. And together it is also called as the input embedding. Okay, so this is the first step that we have discussed right now. And let's go back and look at the architecture. If you look at this part of the architecture, it talks about input embedding and positional encoding. This is exactly what we have discussed right now. So the input gets processed and gets converted into embeddings for every single token in the input. Now, this was existing even before the transformer architecture came into the picture. People knew about embeddings, and in natural language processing NLP domain, this was a very common technique which was used, that every token was converted into embeddings before it was further processed. Even the encoder-decoder architecture was very common for that matter. There was nothing unique there which transformer did. So up until step 2, after creating the vocabulary and then passing the input embedding to the encoder, we are not really doing anything unique. This was already existing previously in literature. The main contribution though comes in step number 3. Now in step number 3, I am going to explain something very unique to all of you. Let's focus on that thing first. Okay, so let's look at the first token, which is the in the sequence. Now, this is something which we have the embedding already created. So now we are talking about further processing that input embedding which has already been created. And the input embedding is represented by this black rectangle. In our example, this has 3 dimensions because it becomes easy for us to visualize the 3D vector. So imagine that this is some vector in space. Imagine that this is some vector in space which looks something like this. Okay, now what happens in the next step is, for this vector, we convert this vector into queries, which is what this Q symbol means, keys and values. And similarly, we do for the token red and the token car. So essentially what happens is this the vector, we further bifurcate it into three vectors. This is the query vector. This is the key vector. And then we have one more vector, which is the value vector. Now, what do these query keys and values exactly mean? This is where the main contribution of the transformer paper comes in, which is the attention mechanism. So before we understand how query keys and values are related, let's take a example and try to understand it. So we'll take the example, the dog chased the car. When I look at this sentence, all of us form an image in our mind, right? Like the dog is running behind the car. So we understand that this dog and this car are related to each other. And this dog and chased are related to each other, and probably chased and car are also related to each other. So in our minds, we are forming these connections without even thinking about it. And these connections are called as attention. So it means that the token dog is attending to the token car. The token chased is attending to the token car, and the token dog is attending to the token chased. So when we understand the semantic meaning of a sentence, we understand which tokens in the sentence are attending to which other tokens. And is the attention strong, is the attention less, etc. Now to calculate the attention for all these tokens with each other, what we can do is we can simply form a matrix which looks like this. Let's say we write the sentence, the dog chased the car, and we write the same thing on the x-axis also, the dog chased the car. Now let's try to draw some attention. Probably fill this. Okay, so the and the probably has some attention. The and dog also has some decent amount of attention. I'll reduce this. Then the and chased has, I don't think it has a lot of attention. So we can reduce this value. Then the and the are, this is same. It's going to have the same. The and car also has a decent amount of attention. Okay, now the next word is important. We are looking at dog. So dog and the, this is going to stay same as this. So we'll copy this over here and do this. Dog and chased probably have a, I'm pretty sure the attention is much higher. So we can increase this to a high value. Uh, we can increase this to a high value. Dog and the is probably same as this first one. So we'll keep this here. And dog and car also has a very high attention, because in our mind we form that picture, right, that the dog is chasing the car. Then chased and the is already filled. We can put that same attention here. Chased and dog is also already filled. We can put that same attention here. Chased and chased probably has a small attention. Chased and the, we have filled it here again. And chased and car has a very high attention because we know they are related to each other. Now, the and the we already know. The and dog, we already know that. So we have already done this for the actually. You can simply copy paste this. And for car, we have already done most of the things. If you look at this car and the, then car and dog, car and chased, again car and the, car and car, I'll probably keep the same thing. So this is something which is called as the attention matrix. And this I have right now formed with just some simple intuition, right? That in my mind, this is what I'm doing. In a split second, our mind does that. But in this paper, they figured out what is happening in that split second. And now to find this attention score, we have to construct the same token is repeated two times, you see, one on the rows and one on the column side. Now, this side, these are called as the queries. So if I take the query then what is the relation of this query to the key the? What is the relation of this query to the key dog? What is the relation of the query key to the key to the query? What is the relation of the query the to the key chased? So all of these tokens on this side are the keys and these are the queries. So you can remember this as something like query is something which is asking a query. How much are you related to me? How much are you related to me? And it is asking that query to the token which is called as the key. So the attention matrix is formed from the queries and the keys. And you can actually do the same thing for the red car and it probably looks something like this. You can see here I have constructed the attention matrix for the queries and the keys. And here, let's say for each query, I have three values. Or let's not use the word values, let's use the word scores. For each query, I have three scores. For query one, I have a score which is coming from the relation of query one with key one. For query one, the second score is coming from the relation of this query with key two, etc. And you can see this magnitude of these attentions are different. That is why the intensity of the color which I have shaded them by is different. So the other word for this is also called as self-attention. Because every single token in the sequence is attending to every other token in that sequence. That is why it's called as self-attention. It is like that sequence is attending to itself. It is understanding how the different parts of the sequence are related to other parts of that sequence. Now, what we do after this is let's focus on this query. We have calculated the attention scores for this query, which are three attention scores. What we do is we take these three attention scores and we multiply them by the three values v1, v2, and v3. And we get this modified vector for we again get modified vector for red and we get a modified vector for car. So let's look at what's happening to this token Imagine that you are this token. The first thing that you do is you wear an uniform which maps you to an embedding, which is the input embedding and the position embedding. Then what you do is you ask a query to all the other tokens in the sequence by asking them, how much are you related to me by? You calculate the scores and then you multiply each value for each token with that score and you add up that product and you transform yourself to a vector which is called as the context vector. So finally you get these three context vectors at the end of this layer. So this is the context vectors. Remember, we started out with three vectors here. Again, we have ended with three vectors. But this time, these vectors are capturing the context which they have in the particular sentence. Okay, there is a question in the chat which says the value is not clear. So the value is something which is very interesting, right? Like it's not just enough to calculate the scores. Imagine that you are the query the and you ask a query to all other tokens and you get the attention scores. What next? The attention score is a value which captures how much is the query related to other keys. But finally, you need to transform that query into something which is capturing these attention scores. So let's imagine that the attention score for this is 20, or let's say this is 20, this is 1000, and this is 10. So what this will do is my entire focus will be placed on this token red. How will that happen? What I will do is I will take 20 from here. I will multiply that by V1. I will take 1000. I will multiply that by V2. And I will take 10 and multiply that by V3. So now this 1000 is a very high value, which means that we are focusing a lot on this value which is coming from the token red. And I will modify the, so this is for the vector, and the final vector you get is the context vector for the. Now you see what we have done here. The context vector for the token the is attending, or most of it, maybe 80% of it is coming from the value vector for the token red. So after the embedding stage, the tokens are just uniforms, right? They don't care about what are the other tokens in the sequence. But once you go through this self attention layer, you suddenly understand that, okay, there are 100 tokens, but 95 tokens are not important for me. Only 5 tokens are important for me. And I'm going to update my magnitude and direction so that I am closer to the tokens which are more important to me. And I take that information into account to update myself. So finally, the context vector contains the information about which other tokens are related to the token which we are considering. And this happens for all the tokens. This not just happens for though, it happens for red, it happens for car. It happens for every single token in the sequence. So if someone just looks at these context vectors, they might say, okay, finally they are just vectors, right? But the values of these vectors, the direction is significantly impacted by the attention scores. The vectors are now capturing their context. They know exactly which other vectors they are related to. And that information is being captured. So in this screen, which points are representing V1, V2, V3? So V1, V2, V3, this question is asked by Avishek. V1, V2, V3 are represented by these rectangles here. V1, V2, V3. This figure is not representing V1, V2, V3. This figure is representing the modified vectors for all the tokens in the sequence. Now, if you were to interpret this geometrically, there is a very nice geometric interpretation for this. Let's try to look at, if we imagine these values as vectors. Okay, this is the first vector, let's say. This is the second vector and this is the third vector. Imagine that we are considering that this is red and this is car. This time these are value vectors, okay? So these are V1, V2, V3. This is V1, this is V2 and this is V3. Now I'm going to explain you geometrically how these vectors are transformed. Now imagine that for the query the attention for this is 20%. The attention for this is 80%, 80%, let's take it 60%, and the attention for this is 20%. What I will do is I will construct another vector which is 20% of this. It is probably somewhere over here. Take another vector which is 60% of this. We'll take another vector which is again 20% of this. And I will add all these vectors together so that I'll get the final vector, which probably looks something like this. Now, this is my final context vector for and I do the same process for all the other tokens in my sequence. So I'll finally get three context vectors, right? Through this process. One for one for red, and one for car. So in case you're not able to follow this textual explanation, you can always think about it geometrically. We are taking a linear combination of all these vectors where the proportion assigned to each vector is determined by the attention scores. And then finally, we get these context vectors which capture the rich semantic information in the sequence. Okay, now this is something which is called as self-attention layer. Now let's go back to the transformer paper and see if we can understand this. After the input embedding, it goes through a layer. Here it's called multi-head attention. I don't want to go into that specifically right now. We can discuss about it later, but it will break the flow of the lecture. So you can just imagine this to be an attention layer, but instead of one attention matrix, you have multiple attention matrix in the actual transformer. So it goes through this attention head, which is also, you can call it as a self-attention layer in this case. Okay, so this is the next step. Now what we do is very interesting. Once we have the context vectors, there is a step which is called as a feed-forward neural network. In this step, what happens is that we take each vector, we project it to a vector of higher dimensions, which is generally twice the dimensions of these context vectors, which is 6 dimensions, and again bring it back. So this is typically a neural network, which is a multi-layer perceptron. The input layer has, in this case, let's say there are 3 neurons here, and there are 6 neurons, and then again you bring it back to 3, and you connect all of these with lines. Every single neuron will be connected to every other neuron with lines. This is a multi-layer perceptron with one hidden layer here of dimension 6. And this is a standard practice which is implemented in this layer, which is called as a feed-forward layer. So essentially, we have looked at all the 3 blocks, right? We have looked at input embedding, we have looked at attention, when we have looked at feed-forward feed-forward networks. And this is just a summary. First, we have these input embeddings, which are uniforms, which are given to all these tokens. And at this point, the tokens have no idea what are the other tokens with me. So let's say you're wearing the uniform, you're going to the school, and you don't know how many people are there with you, how many students you have in the school. But then suddenly you realize, okay, I have 50 other students with me, but I am going to make friends with only 10 of them, and the rest of them are not important to me. So then you modify yourself with that information and you change yourself. And this is happening in this next layer, which is called as the multi-head attention. The dimension still stays the same, you see here. And then you pass it through a neural network, which increases the dimensions and then again brings it back. So the purpose of the encoder is to read the source sentence, which is the red car, and create a rich numerical representation of it that understands the context of each word. Remember, we had discussed about encoder in the variational autoencoders also. And there, what we had discussed was the encoder takes in any image and creates it into a latent space. This is also very similar to that. We are also taking an input sequence and converting it into a latent space, which is capturing the hidden factors of variation or the context of that space. The only difference between an image and this is that here we have a sequence, right? So every tokens in the sequence speak to every other tokens. So they are related to every other tokens. And we have to capture this relation also in the sequence. Now, encoding was very popular in natural language processing since a long time, but people had not found a way to capture these long range dependencies between tokens in a sequence. So let's say there are 100 tokens in the sequence. Attention mechanism is a great way to capture the dependencies of every token with every other token in the sequence. People initially used recurrent neural networks, which was extremely computationally heavy and it was not scalable at all. The beauty of transformers is that it's extremely scalable and the accuracy actually increases as you increase the number of transformers in a large language model. So the scalability people only realized after this paper came out. People tried it for different applications and it worked out really well in all these different applications. So the goal of the encoder, as we discussed, is to create a rich numerical representation which understands the context of each word. Now we come to the next block, which is the transformer decoder. Before we move to the next block, let me take a quick pause and ask if there are any doubts in this part. So the
Yes,
question,
a very good explanation. Really appreciate everything you are helping us understand. I still can't understand intuitively what is value. I got very clear understanding of
okay,
query and key. If you can make it very, very simple, I really appreciate that. Thank you so much.
sure. Yeah. So in order to do that, let me actually walk you through one very interesting interactive demonstration. Okay, so for a second, just clear your mind of all the discussion that we have had and focus on this visualization that you see in front of you right now. It looks very involved, but all of us will be able to understand this very clearly now. Okay, so let's say the input sentence is empowers data visualization empowers users to. This is the input which we want to encode. So let's look at the first step, which is the embedding. In the embedding step, as I discussed, every single token is converted into a token embedding and a position embedding, and you add both of them together. So this was the uniform which I talked about. In practice, we don't have three dimensions, but we have high dimensional space, which is of 768 dimensions. But that's not really important. What is important is this process of token embedding and positional embedding. So you can see data corresponds to the position 0, visualization corresponds to position 1, then it goes on sequentially. Now you create the input embedding, that's all right. After that, I discussed that we need to convert every token into queries, keys, and values. Now, this is what happens here. Data is converted to queries, keys, and values. And this is something which happens before the attention scores are calculated. This happens for every single token. Now, the intuition for creating values is something like this. The okay, so there could be an argument which you can make is, why do you need values in the first place? Why can't you directly pass the input embedding itself as a value after you calculate the queries and keys? And that, in fact, is a very valid question. Even I was thinking about it before I went through the transformer paper. So it turns out that the input embedding does not really capture the entire semantic information which is there in your sequence. And to do that, you need a separate vector which is learnable. So this all these vectors are actually learnable, which means that you train your model so that you learn the query keys and value vectors. So my understanding is that the value vector, it encodes the semantic information related to that token really well, and it helps. And I think when they were trying to do the research in this paper, they were probably value vector is not intuitive. I agree with that. It doesn't come intuitively. You can directly pass the input embedding. But it worked out well that they created a matrix which was learnable. So once you create these query keys and values for all of these tokens, you can see that it is vector 2304. Why is it 2304? Because remember, queries is also a three-dimensional vector, key is also 3, and value is also 3. So you have 3 plus 3 plus 3, that is 9. Similarly, in this case, it is 768 plus 768 plus 768. So after you create these input embeddings, you create query keys and values, and that's where it gets interesting. You can see this attention score they have constructed over here, in which the queries are all of these tokens and the keys are also all of these tokens. And for every query, you are asking the question, what is the importance of the key? Is this key relevant to me or it is not relevant to me? And you are building this attention score. So this is what is happening internally. Okay, so and the magnitude of this indicates which query. For example, you can see this is very high, which means that the query data is related to the query to the key data. This is also very high, which means that the query visualization is related to the key visualization. Then this is surprisingly high, which means that users and visualization are related to each other. Now, calculating the attention scores is not enough because we need to scale the value vectors proportionally so that we get the context vectors out of it. And how that is done is over here. I hope you can see this. The attention matrix, which appears over here, multiplies with the value vectors to get the context vectors at the end of it. So what's internally happening is, let's consider the query data. You are taking this attention score and you are multiplying it by the value of data. You are taking this attention score and you are multiplying it by the value of visualization. You are taking this, multiplying it by a value of them, and you are adding it all together. And finally, you get a context vector for data. Similarly, you do for visualization and all the other tokens which come in this sequence. Now, this is a very nice explanation which will help you revise all the concepts that we have taught. Please go through this after the lecture so that you revise everything that we have taught, and you can even change the sentences here at the top. of this, and you can see how the visualizations change as the sentences also change. One thing you might be noticing here is that why is the attention matrix gray in all these areas? It's not even showing any values, right? And this is something that I will explain, but just observe it for now that it's Sriharsha says causal attention. Yeah, interesting. Let's discuss about that as we go along. But just observe this that it's red beyond the diagonal. Below the diagonal we have different colors, but beyond the diagonal it's red, which means that here it's green, it's gray, it's inactive, and to the left of the diagonal you see all these values. Once the context vectors are done, you pass them through an MLP and you get these vectors out of it. So this is how the MLP looks like. You can see here the MLP is projected to a space of 3072 and then again projected back. Okay, so these are the layers which are connected to each other. Shreyas says future tokens removing the attention. Yeah, it's actually correct, both of them, but we will understand that causal attention or this gray, whatever you see, it does not happen anywhere in the encoder. In the encoder, every single query attends to every other key in the sequence. We do not set any values to zero like they have done over here. Okay, so until now we have just captured the semantic meaning of every single token as an output of this encoder. Okay, every single token is mapped to a context vector which captures the information about that token. And this is exactly what the transformer encoder does. Now we will move to the next step, which is the transformer decoder. This is where the actual decoding happens. Remember, an LLM is called as auto-regressive, which means that the LLM is generating the answer one token at a time. So it says something like this, the answer to this question is X. So all these tokens are generated one step at a time. And we also call this process as decoding. So this decoding is done by the transformer decoder. It is not done by the transformer encoder. Let's try to understand what the decoder does in detail. So let's take the example that the input to the decoder is the following. This is the input to the decoder, where the first token is the beginning of the sentence, BOS token, and the second token is car. And I want to predict which is the next token. That is the question I am asking to the decoder. In the encoder, we did not ask any questions like this. In the encoder, the job was just to encode the sequence. That's all. In the decoder, we are trying to decode it back. Not back would not be the right usage, I would say. We are trying to decode it so that we match our target. In this case, we want to swap the objective, the adjective and the noun, right? So we know that after car, we should get red. But then let's see what the decoder does and how it generates the next token in the first place. Let us try to understand that. Okay, so now if you look at this decoder step, which is over here, we have now covered this left part of the diagram and we are moving to the right part of the diagram. The first step of the decoder is again to convert this into input embeddings. So this I have deliberately skipped here because we have already discussed this previously. So imagine that you wear a uniform for BOS, beginning of sentence, and for car also. That's same as what we do for encoder. Next, what we do is we create queries, keys, and attention for all the tokens which are generated at the moment. So at the moment we have BOS and car. So we create the queries, keys, and values for all of them. So here you see the attention matrix is only 2 by 2 because only I have only two tokens. Okay, now what I do is I look at this query which is coming from car and I want to generate a context vector out of it. Now you know exactly how these context vectors are generated. I take this attention score, I multiply this by V1 and I take this attention score and I multiply this by V2 and I add them up together. It looks something like this. So I focus only on the context vector for the token car. Okay, so I get a context vector. Now what we do is after this stage, so up until now we have only looked at this embedding and attention mechanism, which is the first part of the transformer decoder. All of us will understand this. The question which you might have is, we did so much hard work in the transformer encoder, right? And we very painfully encoded everything into these context vectors. The question is like, how do we use that information in the decoder? So our encoder is understanding that the input of the sequence is red car and I want to now predict car red. So the decoder should have that information access. Otherwise, it's just relying on nothing basically. We need to somehow pass the output of the encoder to the input of the decoder. Now, how that is done is very interesting. Let us try to understand it. Please pay a very close attention to this. So this is something which is called as cross attention. Why is it cross attention? Because we are calculating attention scores from inputs which are coming from the encoder side as well as from the decoder side. Okay, so let's look at from the encoder what we have. From the encoder, these black bars you see, these are the context vectors which are coming from the encoder side. So these three are the context vectors. And we use them to calculate the keys and values. Not the query this time because the query is coming from the decoder side. But only the keys and values are coming from the encoder side. So we calculate the keys and values for all these tokens which are the red and car. And this is how the attention matrix looks like. This is the token that we are currently focusing on. And the query actually comes from this. So I'll denote this as Q. And we have three tokens which the query asks the question, how important are you to me? How important are you to me? And how important are you to me? And we know that this red is the most important because this is the word which is supposed to come next. So if you look at the attention scores here, it should probably be like this. How do I now create a context vector for this based on the attention scores? We use the exact same thing we did before. We take this, we multiply this by V1. We take this, we multiply this by V2. We take this, we multiply this by V3, and then we add them up together, which is exactly what is done here. And finally, you get the context vector for the token car. And now this token car, again, the dimension is exactly the same. It's a three-dimensional vector, but let's try to understand this geometrically like we did before. I think that will be give another way for us to think about this. So let's say we are working with three dimensions. Okay. And these are the three value vectors for this is value vector 1. This is value vector 1 and value vector 2 and this is value vector 3. Now these vectors are corresponding to not the tokens coming from the decoder but coming from the encoder. So this is red and car. And all these value vectors are coming from the encoder side. Now, let's say this was our original query vector, which was coming from the decoder side. It's called car right now. How this gets transformed is you look at the first value vector and you multiply it by this attention score. So it becomes this. You look at the second value vector and you multiply it by a stronger attention score. Looks like this. And you look at the third value vector, you multiply it by again slightly strong attention score. It looks like this. And cumulatively, you add these vectors together, you get a vector which looks something like this. Now, this is the context vector for car. This is how the vector gets transformed from here to here. And this layer is called as cross attention layer. Why is it called cross attention layer? It is because we are only using the tokens from we are using the tokens from the decoder side as well as from the encoder side. So it's not just attending to only tokens in one sequence, but it's attending to tokens which is coming from some other sequence. That's why it's called as cross attention. Okay, so this is great. And then after this, again, we have the exact same step, which is that of the feed forward neural network. We project it up and we project it down. And then we get a context vector at the end of it. Okay, so there are some questions with respect to are K and V from encoder reused in encoder self-attention or this computed? No, so the K and V which are coming from these are not reused. These are recalculated using the learnable weight matrices on the decoder side. We don't directly use it. We only use the context vector from the encoder. That's it. But these keys and values are recomputed again using the learnable weight matrices coming from the decoder side. So they are not reused. And about the BOS tokens, we start with the BOS token itself. So this is not predicted by our model. This is something that we just start out with. Okay, so now after this is done, let's look at the architecture again. First, we saw that, okay, we are creating embeddings. Then we are doing the attention mechanism, which is the self-attention mechanism. Same as we did for the encoder. We create some context vectors for the current token, which is car, only for the current token. Then we create another layer, which is called as cross attention layer, where the query is coming from the current token, but the keys and values are coming from the entire sequence in in the encoder. And then we calculate again the context vector for this current token. We pass it through a feed forward layer. So most of the things are same. The only thing which is different is there is an additional cross attention layer which is added on the decoder side. Okay, so let's try to understand one last step which is pending. That is Okay, that is you might be thinking we have created a context vector for the token car, but how do I generate the next word? How do I generate the next word which is red? I have not discussed that before this point. So the last step is remaining, which is called as projection into the vocabulary space. This is a very important step because this is something which has become the hallmark of modern LLMs, which is next token prediction. So what we do is we have this context vector from car, which is coming out after the self attention, cross attention, feed forward network. So it has gone through a lot of manipulations and transformations. We project it from the three-dimensional space up to 21 dimensions, which is our entire vocabulary over here. So this is our vocabulary: white, blue, green, yellow, black, red, orange, then some objects and beginning of sentence, end of sentence, pad, and UNK means unknown character. And you look at this and you see that, oh, okay, red has the highest value, so my next token is red. And this is exactly the last layer which you see here, which is linear and softmax. So usually what happens is when you convert this into the projection or once you project it into the vocabulary space, you get values for all of these like 30, 40, 50, 120, etc. And then you apply a softmax layer to convert it into probabilities between 0 and 1. And you pick the token which has the maximum probability. That is why LLMs are called as models which predict the next token which has maximum probability. So here you can clearly see that the token red has the maximum probability. So I will choose that as the next token which is coming in my sequence. And then I will continue. I will add it to my sequence. I will predict the next token, again add it to my sequence, again predict the next token, etc. And this process will go on until I reach the end of sentence token. So this is the entire framework which we see in the transformer architecture, which is the encoder and the decoder. Now, very interesting thing is that LLMs like ChatGPT do not use the transformer encoder at all. They only use decoder. That is why they are called as decoder based architectures. Can you think of some examples where we also use the transformer encoder? In which practical cases do we will we need the transformer encoder? Yeah, Abhishek has given a perfect example for this, which is translation. Imagine that you have a task where you ask the question, I am in India. Okay, and you want to translate this to Hindi, मैं इंडिया में हूँ, मैं इंडिया में हूँ. So now what you do is, as the first step, you pass this through a transformer encoder. The encoder will create context vectors for all these tokens. How many tokens are there here? Let's say there are 4 tokens. Okay, there are 4 context vectors which are created. Now you can see here, uh, if you look at the self-attention matrix of this, you see the long range connection here. I and India are will have some attention score, and I and am will also have attention score, and in and India will also have a high attention score. All these inter-token relationships will be captured by the attention block which we have within this encoder. Okay. Now, what we do is once you do this step and you have encoded this information which is coming in as an input sequence, we have the next block which is the decoder block. Now, in the decoder block, what will happen? Let's try to understand that. In the decoder block, first I will pass the BOS token as an input. Okay. The BOS token which will first go through self-attention with itself. It will modify its values with the self-attention. And then what it will do is it will use the keys and values which are coming in from the encoder side and it will do a cross attention. And then it will pass it through a feed forward network. It will project it into a vocabulary space and it will give an output at the end. The output will pick is the one with the maximum probability, which is, let's say, may. Now you see the interesting thing is if we did not have this cross attention with India with this sentence, how will we know that India is supposed to come next here? Because India is coming fourth in this sequence and second in this sequence. But because we are learning this dependency within this sentence and also between these tokens and these tokens with the cross attention layer, we know that I and India has a high attention score. That is why it's much more likely that in the translation, India comes next. So this happens. So you have first May, then India, then India, May, who. So it happens one one pass at a time. You do one pass, then you get India, then you do another pass, you get May, and then you get who at the end. So translation task is something which you cannot do without an encoder and a decoder. You need both of these architectures to do it. Okay, so now these are the encoder-decoder architectures. Let us take a pause for some time and we will move to the next part, which is how do we apply these architectures to robotics data exactly? So I'll stop sharing my screen and I will take questions now at this moment.
Hi, sir. Vishaka here. Just one basic question, no? So,
Yeah.
can we say transformer is either encoder or decoder or combination of both based on the requirement?
Yeah, exactly. So we can either have a transformer encoder architecture for an application, we can have a transformer decoder architecture, or we can have a combination of both. So if you
Okay.
look at the original transformer paper, they show both the things together at a single time. But if you use if you look at ChatGPT or other LLMs, we are generating one token at a time. So for such applications, we only use the transformer decoder and not the encoder.
Oh, yeah. Got it. Thank you.
Yeah, thanks. Okay, can anyone think of, we looked at sequence modeling, right? That we have a bunch of tokens which are coming in as a sequence, and we are either capturing the semantic information or we are predicting the next token. How does this apply to robotics exactly? What is the sequence over there?
Motor positions.
Yeah, exactly. So in robotics, we have sequence of actions similar to how our large language model predicts the token one at a time, which are also called as actions. Similarly, when we look at any robotic arm, we are the output is the actions which are predicted one time step at a time. So initially you have the motor positions for all six angles, let's say. Then at the next time step, you have different motor positions. So you see a trajectory there for every single joint. So wherever we see a sequence of trajectory, it can be either tokens coming in from language or it can be numbers from your robotics data. It's a sequence. And exactly the input to the encoder for the robotics is not just a sequence of proprioceptive data, but also sequence of images data. So somehow you need to have a mechanism which encodes both images as well as text and then passes that information to the encoder. So very interestingly now, this you can think of before we meet in the next lecture. ACT architecture, action chunking unit transformers, they use a transformer encoder and a transformer decoder. This much is fine. But they also use a variational autoencoder. How would you make sense of these three being used together? So far, we have looked at VAEs separately, transformer encoder decoder separately. But action chunking with transformers actually merges both of them together. So this is something which we will encounter in the next lecture, but you can think about the architecture for ACT. Or what we can do is before the next lecture, uh, if you can just think on your own with this information that we have, how will you build a robotics model using the VAEs and transformer architecture that we have looked at? What will be the input? What will be the output? So I will discuss that before we meet next. If anyone has any diagram, then you will be asked to share your screen and explain it. It will be very, very useful for us before we look at what is done in the paper. If we can even get to 60-70% of that without looking at the paper, we'll have a great time understanding the paper itself. So let's see the chats. Maybe images goes through VAE and text go through transformer. Uh, yeah, that is not the correct answer actually, but I will let you think about this more.
Maybe
But
latent variables goes to the transformer.
that's actually correct. The latent variables goes as an input to the transformer encoder. You would think that the transformer encoder generates a latent variable, right? But the
Maybe
variable itself goes as an input to the transformer encoder.
So I
I don't
haven't
think
got
it.
the question properly. Can you please
Yes, yes. So
explain
the
if
question
not?
is, yeah, the question is that we have looked at VAEs and transformer encoder decoder separately. And in action chunking with transformers, they use a VAE as well as a transformer encoder and a transformer decoder in their architecture. So the question is that without looking at the paper, VAE, the ACT paper, can you guys come up with an architecture which can take the proprioceptive data and the images as an input and predict the robotic actions as an output using all of these three together?
Is the VAE is being used for generating the latent variables and then that is sent through the transformer encoder. Then we use that for the decoder.
That's actually correct. Yeah.
Okay.
So broadly speaking, what happens is the VA is used to generate the latent variable, and then that latent variable is passed as an input to the encoder, transformer encoder. But are you saying that that's the only input to the transformer encoder? Or what else can be the input to the transformer encoder?
The conditional.
Because we are already passing the images and the joint angle data as an input to the VAE encoder. So do we need to pass it again to the transformer encoder or no? Actions. Vishaka says actions. And uh, instructions on what we want the robot to do. Okay. So we have recorded episodes, let's say, of human demonstrations, and we want to use imitation learning. So we don't want to give any explicit instructions, but we want the model to be structured such that it learns from this human demonstration data. So first of all, the one clarification here we should make is we will have a different architecture for training and we will remove something for inference or testing. So you need to think about that also. What will we use for training? What will we use for testing? Because I think Vishaka suggested using actions. So you can't use actions for testing because you will not have access to them. That is something you are supposed to predict. For every observation, you have to predict the next actions. But we have access to actions during training, right? Because some people have actually collected the data. So we can use these actions for training, but for testing, we don't have access to them.
For testing, we just have the visual data, the distribution, something like that.
Exactly, yeah. For testing, we have not just the visual data, but we have the joint angle data
Yeah,
also.
yeah, of course, yeah, the current position of the
Yeah, yeah,
motors.
the current position, yes. Okay, so let's discuss this again in the beginning of the next lecture. And now let me share my screen and we'll move ahead. Okay, so in the field of robotics, we will mostly be working with image-based data. And so far we have looked at sequences of text, right? But how does this translate to images? Images don't present themselves as a sequence. We just have an image. Text very naturally presents itself as a sequence. We know that something is coming next of something. But images is like you have a bunch of pixels you see at once, all of them together. You don't think of them as this comes before this comes after this, etc. And after the Transformers paper was released, people started thinking about, can we use the same architecture for vision related tasks? And it was not very straightforward on how to implement the transformer architecture for vision. Because first of all, we have to create some sequence, right? And we are predicting the next token. So what are we predicting here? So let's take an example. We want to perform a classification task. Let's say there is a painting which is drawn by a famous artist, and we want to identify who has drawn this painting. Now, transformer decoder gives you the next token. So probably that's not ideal for this. That's the first thing we understand. The second thing is maybe transformer encoder is ideal for this because it captures the information about that image. But the encoder finally gives you the context vectors for all the tokens in the sequence, right? How will you classify the image? So you have two problems. First is how to present this image as a sequence. And the second is how to classify the image. So we will be looking at how both of these issues were tackled with the famous Vision Transformers paper. Okay, so let's take an example. We will take an example of one of the observations collected from our robot. And let us say okay, Pramod says something interesting, taking first or last context vector. But why are we biased by first or last? What is so special about them? Okay, let us say that this observation looks like this. Okay, which you have collected from the data. This is the image that we are working with. From this image, we can probably guess that the camera is mounted somewhere in front of the robotic arm. And the task the robot is trying to perform is to place this golf club into the orange cup. Okay, so this is the image that we have. Now, first let us discuss how to convert this into a sequence. And that is done using a very simple trick. We divide the images into patches, which look something like this. One image divided into 9 patches. And then you can, so these are like 9 tokens. 1, 2, 3. Very simple, right? But it's the simple things which are very scalable. In most of these papers, you will see that this is something which might come to our mind also if we start thinking about how to extend the transformers paper to vision transformers. Okay, so now we have these 9 different tokens, and these are not text tokens, that is fine, but anyways, we are converting the text to an embedding. So similarly, why can't we convert every single patch into an embedding vector? So we do not have tokens here, but what if we take these patches and convert them to patch embeddings? Now, let us say that the dimensions for each patch is 28 by 28 by 3. So let's say this patch is 28 by 28 and it has 3 channels. So totally you have, in one patch you have 2352 values. And now imagine a neural network which takes these values and converts it into a dimension of 5 and 2. This is just a hypothetical example. And this is the token embedding dimension. In our transformer encoder discussion, we had taken an example where we had considered the dimension to be 3. But in reality, as I showed in the animation before, the dimensions is usually much higher than 3. Maybe 5 and 2 is very common, or 768 is also common. So this is the token embedding dimension, which we simply use a neural network to convert these patch embeddings into token embeddings, or to create patch embeddings rather, just from patches. So these are coming values which are coming in from the pixels. And then we are creating embeddings out of them. So this is the first step, which is mentioned in the paper which talks about vision transformers. All of these patches are our input. So there are 9 patches, and these patches are passed through a simple linear layer to convert them into these 9 token embeddings. We do not use any CNN over here. In fact, vision transformers is a alternative to CNN based methods, and in many cases it has worked quite well compared to CNNs. Okay, so now we have these 9 token embeddings. After we take these patches and then we create embeddings out of them. But we are missing something very crucial here that we did for transformer encoder. So we can understand this using a nice example. So imagine that you have these two images. Okay, so this image has 9 patches and this image also has 9 patches. So the number of tokens are the same. And the second image is just rearranged version of the first image. So the token embeddings are also same for both the images. If you look at the entirety of the token of the token embeddings as a set, that set will be exactly the same for both these cases. But the meaning of these two pictures is very different, right? This actually represents a coffee cup, but this does not represent anything. It is something very random. It is like rearranged. The patches are rearranged. So the final output is going to be dependent on the ordering of the patches also. And that is why ordering the patches, understanding the ordering is very important. And we need to pass that as an input. Now, how is the ordering passed as an input? This is the exact same thing we did for transformer encoders also. We converted or created position embeddings for tokens, right? Similarly, why can't we create position embeddings for all these patches? We will call these patch as 1, 2, 3, 4, 5, 6, 7, 8, 9 and create position embeddings for them. And we add it with the token embeddings and that becomes our entire input embedding. So this is exactly what is done here. Position embeddings are calculated and our modified architecture looks like this. First, we create these patches, then we do a linear projection of these flattened patches. And this is the token embedding. And this is the position embedding for each of the patches which we see in the image. Okay, now the next step is actually quite simple since we have understood the transformer encoder well. It is exactly the same. If you look at this, we can pass this as an input to the transformer encoder. Let us understand what happens here. This will also be a nice revision for us to see if we have really understood the concepts well. Okay, but let's look at that after some time because we are missing one key thing here. So how do we use the output of the transformer encoder? Let's imagine that this is done. Let's imagine that this is done. And finally, we get context vectors out of all of this. How will we use these context vectors to classify the image? I want to understand if anyone has any ideas with respect to this. How will you process these 9 context vectors to classify the image? So Vishaka is saying that using attention, Sriharsha says taking average of them and linear projection into num classes. Pramod says CLS token. Okay, so let's understand this. So as it is, all of us understand that this architecture will not work completely because we have nothing to classify the image. So instead of this, what people do is, first let us understand what our encoder will do. Our encoder will take all these patches and convert them to context vectors. Like this first patch will be converted to this context vector, second will be converted, etc. Now we have seen the process inside what happens. We have an attention layer and we have a feed forward layer. and then finally we get a context vector out of it. What will be the size of the attention matrix here? Since we are doing the self attention, every token here is attending to itself, and there are 9 tokens. So the size of the attention matrix will be 9 cross 9. Okay, so the way we classify this image is we add a learnable embedding to the sequence of embedded patches, which is over here, which is called as the CLS token. So we initialize this token with random values, and finally we just look at the output of this token, the context vector for this token. We do not look at the context vectors for any of these tokens. We only look at the context vector of this token which you have added. And this learnable token is also called as the class or the classification token. Now you might be thinking, okay, this is fine, but then is all this computation going to waste? Why are we then passing all these as an input to the encoder if you're only concerned about the CLS token? And how does the CLS token actually have an information of the entire image? So somehow intuitively we understand that if this has to work, the CLS token has to understand every single part of the sequence properly. Otherwise, it's not going to work. So unless it has access to all these other flattened patches and their embeddings, their values, queries, keys, etc., this approach might not work. So let's use the same mechanism that we use for the transformer encoder, but just we'll think of, instead of 9 tokens, we have 10 tokens. So we have a 10 by 10 matrix now. So let's see how the attention matrix looks like. The attention matrix looks like this. Instead of 9 tokens, we have 10 tokens over here with the CLS included, and similarly we have 10 tokens over here. So we have total of 100 values in the attention matrix. Now what we do is we don't look at all these, but we only look at this CLS token, and the CLS token we look at how does it attend to every other token in the image. So how does it attend to this token, this, etc. And this is captured in these attention scores. So these attention scores are actually capturing how is this CLS token related to every other token or patch which you see in the image. And after this, it's straightforward how to calculate the context vector for this. It's the same approach that we have done before. So this is something I've probably not explained here, but this I've mentioned as an in-class activity. So what we'll be doing is, let's say there are 9 of this, right? And the CLS token. So yeah, let us assume that there will be 10 value vectors, which are corresponding to these 10 tokens. So this is one value vector, probably it corresponds to the first one. This is the second one. This is the third one. Now remember, all of these are learnable value vectors. We don't know their values beforehand, but as we train our model, we eventually learn them. 7, 8. So these are 10 of them. Okay, and let's say our initial query, which is the CLS query, it looks like this. Now what happens here is you look at all these 10 and you multiply them by their attention scores. So it gets scaled up or down by the attention scores, depending on the value of these scores. And whatever I'm doing on this graph right now is something which will help us understand why the CLS token captures all the summary of the image. To calculate this final value vector or the final context vector, we are requiring access to all these green vectors, you see, which means that we are requiring access to all these patches. And we are taking a sort of a weighted average of all these patches and creating a final context vector. So this is how the CLS token context vector is calculated. There are some questions in the chat with respect to initial value. So initialization of the CLS token is random. We have no information about the how the token is initialized. And in most of the cases, the patch size is related to the original image size by some ratio. So I have seen different ratios used in different papers. There is no standard value. And then this modified context vector, this is what then after that you pass it through a feed forward network and you create a final context vector. Same as we did for the transformer encoder. Okay, now that we have the final context vector, how do we use to classify it into different classes? So we are probably missing something, right? Imagine we started out with an example that, remember we started out with an example that different paintings you have to classify according to their artists. So here we are just getting the context vector at the end, and that too of the CLS token. How do we use that context vector to classify our images? And for that, it's very simple. What we do is we add a simple classification head at the top of it. So the CLS token, it goes through the transformer encoder, we get the context vector, and then the context vector is projected into these number of classes, which are let's say 5 classes, and we get the final scores for these. So this is given as follows. This is called as an MLP head. So this is also called as a classification layer. So one single context vector is projected into, so let's say this has 5 and 2 dimensions, and you have 5 classes. So you build a neural network that takes in 5 and 2 dimensions as an input and predicts and projects it into 5 dimensions as an output. So conceptually, this is very similar to the projection that we did in the vocabulary space, but at that time that was a huge space. This time it's only number of classes. It's not a vocabulary space because we are not predicting the next token, right? So the number of output dimensions is same as the number of classes that we have in our problem statement. And then we look at, okay, which one has maximum value, and then we pick that as our class for our image. So this is how the final diagram for the vision transformer looks like. Okay, so now we have this vision transformer, which is something you will see being used in the action chunking with transformers paper as well. Because if we are using a transformer and if we are using images, then we need to have a CLS token. So wherever you see a CLS token, you immediately know that there is some sort of embedding being done here. Or if you want to capture the semantic information of an image into a single vector, then CLS token is the best option to do that. So if for any application, we want to capture this image into one vector, so you can't look at all the context vectors which are coming out from the encoder. So you need to append a CLS token at the start and then learn the values of that CLS token through your training. So the question that I asked you a while back is, we discussed VAEs separately, right? And then we discussed about transformers separately, both the encoder and the decoder. And then we discussed about CLS token and its usage. Action chunking with transformers, ACT, which is the policy which we are going to study, it combines all of this. And it combines in a way that the policy very efficiently predicts the action for every observation which your robot sees in the environment. So I want all of you to think about this, because all the building blocks are already in place now. It's just a matter of assembling them in the right way so that we get the final picture in our head as to exactly how these blocks can be assembled and how to make it work. So it's just a small arrangement which we have to do with respect to these blocks, and then we'll get the final ACT architecture ready. And then we'll look at one simple example to understand how this vision transformer is implemented in practice, so that it will not seem a very distant concept to you, but once you see the implementation, it will suddenly seem very real and it will not seem like a distant, far away concept. So I will share this link in the chat. In this link, what I have done is I have used a vision transformer on a specific data set. And this is a simple data set which has different leaf images, and the images have different diseases. So there are different categories of leaf diseases which are there in the data set. And we have to use a vision transformer to classify these images into the right category or the right bucket. And traditionally, if you have done any basic AI course, you would know that for such tasks, CNNs are the most popular technique which have worked. But CNNs are not used in modern image-based applications which involve LLMs, and vision transformers are the go-to. So we are going to use VLMs for a simple example just to get some familiarity with it. Okay, so first what we'll do is we will import this dataset, which is the beans dataset from HuggingFace. And we will split this dataset into training and testing. It's a standard process. And then we transform these images using horizontal flips and crops to make sure that we have different or a lot of diversity in the training data, which is done in this step. Also here you see we are loading a model checkpoint which is called as Google VIT. So if you just copy this and paste it in a separate tab, this is a vision transformer model which is developed at Google, and it is trained on a large collection of images, namely ImageNet 21,000 at a resolution of 224 by 224 pixels. So now you can actually understand this paragraph. It says images are presented to the model as a sequence of fixed size patches, which are the tokens we are talking about, which are linearly embedded. And one also adds a CLS token to the beginning of the sequence to use it for classification tasks. And one also adds absolute position embeddings before feeding the sequence to the layers of the encoder. So this is already a pre-trained model which has been trained on a used data set. All you need to do is replace the classification head of this with the number of classes that you have and fine-tune it for your own data set so that it learns to understand the images well. So here it says one typically places a linear layer on top of the CLS token as the last hidden state of this token can be seen as a representation of the entire image. So this we have already seen actually. We know the model description and how it works now. And this is the paper which is referenced in this link. This was the paper which introduced image transformers to the world. It's called An Image is Worth 16 by 16 Words, Transformers for Image Recognition at Scale. So I want all of you to take a printout of this paper and read this also. So overall, there are 3 tasks. Read the transformer paper, vision transformer paper, and think about how ACT has combined the transformer and VAE and CLS token together to build a policy which is very efficient for robot learning. The reason I am emphasizing on reading papers is because it will really help you get a deep fundamental understanding of the concepts. Looking at a video is very different from reading a paper by yourself. There are a lot of things which are missed in a video. When you read a paper, you get a lot of confidence in that subject. Okay, so now let's go back to the transformers, the notebook. And this is where we initialize the model and train it. It might take some time for you to train. I have connected it to A100 GPU. And then finally, you see this is the final prediction that I get at the end. I got an accuracy of about 95%, where I trained only for 3 epochs. Why do I need very less epochs? Because the model is already pre-trained. I am simply fine-tuning it for my specific task. So the initial accuracy itself is 94%, and it just increases to 97, which is why out of 16 images, I get 15 correct and one I get as a wrong prediction. So whatever is happening here, right, how images are classified, this is exactly what vision language models use. And now if you look at the first thing that we started out with our lectures, looking at these different architectures, let's look at this small VLA for now and try to see if we can understand some of the text which is written over here. Okay, so firstly, let's look at this left box, which includes the input which is passed. Okay, so the input is the task, grasp the object and put it in the bin, which is a text-based prompt. And these are the images which are coming in from the camera, which is the image data. And there is a self-attention which is performed over here. So this is probably the encoder which performs self-attention. And on the right, you see from the self-attention, you pass the keys and the values, which is denoted as KV. And you do cross-attention. It is done 2 times. So now you know why the queries are not coming in from the encoder to the decoder while doing the cross-attention. Because the queries are coming in from the decoder side, which are the actions. So the queries are the actions and the keys and the values is the context vectors for the entire observations which are passed as an input. And then this is their architecture which SmolVLA uses. If you look at, let's say, Groot. So Groot also, if you look at it, the input remains the same, the image observation and the language instruction. And also the robot state, which is the proprioceptive data. In the action chunking with transformers, we are actually going to ignore this language instruction because This is a bit complex. We have not reached that stage yet. We will only include the observation data and the proprioceptive data. So the images is encoded. I think they might be applying some patch embedding over here. Image tokens and text tokens, you see it's tokenized, and it is passed through a vision language model, which is most probably a vision transformer like system we looked at before. So they would have a CLS token here, which the output we will get as a context. And the robot states they are embedding separately. And all of this, the robot states, plus the context vectors coming out from the encoder, they are passed through a vision transformer to a diffusion transformer to predict the motor action. What is a diffusion transformer? We have not looked at before, but try to find some pattern between all of these configurations. Now let's look at another one, which is OpenVLA. What OpenVLA does is, this is the vision language action model. So this is the data, which is most probably proprioceptive data images, which is passed as an input. You have a base vision language model, which is the vision transformer here. And these three boxes that you see, those are probably the actions which my model is predicting. So they have not actually gone into detail of this architecture. It would have been great. Yeah, here it is. So as we had predicted, the input is the input image plus the robot joint state. They have not mentioned here, but it has to be there as an input, and the language instruction, put eggplant in a bowl. Now the images are separately tokenized using this same MLP projector like we had in VLAs, right? We had this projector which converted images into input embeddings. Similarly, we have this projector here, and the language instructor is tokenized using a llama tokenizer. All of these tokens then go as an input to this llama 2 7 billion parameter model, which is trained to then predict the actions at the end. This architecture is very different. I don't expect you to understand it completely, but I want you to understand the terminologies which are used in all these diagrams. So then you predict the actions and then you predict the robot actions at the end of it. So let's try to read this. We train OpenVLA by fine-tuning a pre-trained prismatic 7 billion VLM. Our model consists of three key elements: a fused visual encoder that maps inputs to a number of image patch embeddings. This is exactly what we thought it was doing. A projector that takes the output embeddings from the visual encoder and maps them to the input space of a large language model. So this is happening here in this projector. And a Llama 2 language model backbone that predicts tokenized output actions. So you can see in the VLA's architectures, they are actually using a large language model or a vision language model here. But in action chunking with transformers, we are not going to use any LLM. We are simply going to work with transformer architectures. And then we come to the ACT paper, which is probably mentioned somewhere. Yeah, this is the ACT paper, and I'll not expose you to the architecture right now because we will discuss that in the next lecture before we start it. Okay, so to summarize, I think we are in a great place to understand the ACT policy now, to understand the code and exactly how it works. And this will be a great foundation for us later to do our practical implementation of the robots. So I'll stop sharing my screen and take any questions if you might be having. We do not have a Discord server, but that's a great idea. I will start the server soon, and the server link will be updated on your dashboard after this lecture. So the recordings are actually updated on your dashboard. If you are not able to access it, just let me know, but it's uploaded on your dashboard as a link. After every lecture, we are doing that up in maybe 1 or 2 days. So now this recording will also be uploaded on the dashboard.
Rajat, can we ask questions related to week one?
Yeah, sure. Go ahead. Yeah.
And specific related to the inverse kinematics, can you please walk through in a brief 2 minutes for the inverse kinematics section and the script which you have shared?
Yeah. So inverse kinematics is something I've deliberately stayed away from up until now. But if you are interested in that, I can actually take it separately in the next lecture. Like I'll include it as a part of the lecture.
Okay. Thank you.
Yeah. So because it will take some time to explain it, it involves a Jacobian of the input-output relation, which is the derivative of the output with respect to the input. Otherwise, it's very simple, but it includes a Jacobian matrix. I will explain that in the next lecture.
Okay. Thank you.
Okay, everyone. Let's meet next week. Sriharsha is asking for Miro dashboards for diffusion models. Yeah, some things which are related to this course that I will share. For example, VAs, uh, deep generative modeling, and we will come across some other architectures also which might be related. So those I will share with you, with everyone. I will share on the dashboard. You will see them under the lesson notes section in the dashboard. Okay, everyone. Thank you very much, and we'll meet again next week. Bye.